Thank you very much for the introduction, and thank you very much for the invitation to speak in your seminar. Yeah, so the plan for my talk, so I want to discuss twisted affine Schubert varieties, and in particular, I want to discuss some results about global sections of sheaves on twisted affine Schubert varieties. So the plan of the talk is first to discuss the analog in the untwisted setting that this is generalizing. So this is work of Shenwen Zhu that he completed in, I believe, 2007. So once I kind of discuss the basics in the untwisted case and this work that is being generalized, I'll discuss the twisted affine Schubert varieties, and then I'll move on to the T sigma fixed subschemes. So I'll get to this at that point. So this is a talk in Lie theory. So we're going to have the standard notation that you're going to have in any standard Lie theory talk. So I'm going to fix a maximal torus inside a Borel subgroup inside of a reductive group G. All of this will be taking place over C. Associated to this is going to be a root datum. So I'll use the omega I checks for the fundamental co-weights. I'll use the alpha I checks for the simple co-roots. I'll use the omega I's for the fundamental weights and the alpha I's for the simple roots. And then I'm going to be working with the field of formal Laurent series. So this will be denoted by K, and then O will be the ring of integers. So this is a formal Taylor series. So this is the notation that I'll be using. And now I can begin. One more thing, I won't be able to see the chat, and if something happens with the camera, please let me know vocally. One more thing for notation. For a given lambda, so if lambda is a co-weight, so lambda is a co-weight, then I naturally induce a point inside the k points of the torus, which is going to be called t to the lambda. Okay. So then we come to the topic. So we need to talk about affine Schubert varieties and affine Grassmannians. So first, definition. The affine Grassmannian, which I denote by G, this is going to be equal to, at least on the level of C points, to G of K modulo G of O. Now, in this work, something that I'll be focusing on a lot is either T fixed subschemes or T sigma fixed subschemes. So a definition on the level of C points isn't quite enough. So we need something a little more schemy. So I can give a moduli description of the affine Grassmannian. So if I let dr be equal to spec R double bracket T, where R is a C algebra, and then I'm going to denote the punctured disk dr. This is going to be equal to spec R Laurent series in T. D. Then I can give a slightly better definition of the affine Grassmannian as follows. This is a kind of a moduli description. I can also define the affine Grassmannian, the R points for R of C algebra, to be equal to the collection F of G torsors over the R disk, and beta, a trivialization, so that beta is a trivialization of F. So F is a G torsor. This will be trivialized on the punctured disk. So when I restrict F to the punctured disk, it's going to be isomorphic to F naught, the trivial G torsor on the punctured disk. I just write this not because we need it so much right now, but because constructions of this nature will come up later, and this is kind of the setting in which we want to be working. Okay, so I'm now going to come out with a bunch of facts. So facts. So the first is that the affine Grassmannian is an in scheme. That means someone's joining. Okay, the second fact that I want to use is that if G is reductive, so G reductive implies that G is ind projective. So since we're always going to be working with G reductive, we always know that the affine Grassmannian will be ind projective. However, we will need to deal with some possibly non-reduced structure. So the next fact that I want to state is that, so fact 3 is that G being reduced is equivalent to having trivial homomorphisms from G to GM. So immediately we can see that, for instance, if G is simple or semi-simple, then the affine Grassmannian will be a reduced in scheme. But there's a very important example that will be important is the torus. The torus has plenty of characters. And what this is telling us is that the affine Grassmannian for the torus will be a pretty highly non-reduced in scheme. And that non-reduced structure will be important. So if you just look at the closed points, so T is going to be isomorphic to the co-character lattice as, well, maybe I'll say closed points. But sitting over each of these closed points is a very intricate non-reduced structure. So the affine Grassmannian for a torus is an important example to keep in mind. The next fact that I want to mention is the following, that if G is simple and simply connected, then the Picard group of the affine Grassmannian is easy to describe. The Picard group of G will be isomorphic to the integers. And what I can do is I can pick an ample generator. So I'll denote L, so the ample generator. Right, all these things are in projective. I'm going to have some ample generator, so I'm going to write that L.
Mark, may I jump in here with a question?
Yeah, absolutely.
If you divide your non-reduced scheme by the nil radical, is that the same thing as just taking your reductive group and dividing by the radical and getting it to be semi-simple, or is it something more elaborate than that?
So you're taking a
non-reduced scheme. It has all that nilpotence. You can divide,
right.
And then you do a reduced scheme. Would that be equivalent to replacing G by G mod the radical or something like that, or is it more elaborate than that?
I think it should be kind of something delicate. I'm not exactly sure, but I definitely have in mind a picture in some cases of what the full non-reduced scheme structure is, and then if you divide out by all the reduced stuff, the picture in my mind roughly is that that should correspond to. So I don't know how to view just this thing on its own as the affine Grassmannian of something.
All right.
With its reduced, just a discrete collection of points. I don't know how to view that as an affine Grassmannian of something. I'm not sure if that answered the question, but anything further?
No, thank you.
Sure. Okay, so there won't be very much Kac-Moody theory in this talk, but one important notion that I'll bring up right now is that these affine Grassmannians can also be realized as quotients of affine Kac-Moody groups. And the only reason I bring that up is that allows me to define a homomorphism called the central charge homomorphism. So I have a homomorphism C from the Picard group of Ger G to Z. And the fact is that the central charge of the ample generator is equal to 1. So this will be a very important fact. Essentially, I will always be dealing with line bundles L of central charge 1. That's very important for this story. And this is always going to hold in this loop group setting. Okay, then we have a bunch of geometric facts about affine Grassmannians. So there's a stratification. So we can write Ger G is going to be equal to a disjoint union over lambda inside the dominant co-characters of these double cosets, G of O, T to the lambda, G of O, mod G of O. This fact comes from the Cartan decomposition or the Bruja decomposition. Every time that I give a talk like this, either one of my professors will argue about what I should call that. Okay, and so these cells are going to be my my Schubert cells. So by definition, the Schubert cell, I'll write this Ger lambda, Ger G lambda. This is going to be this double coset quotient, G of O, T to the lambda, G of O, mod G of O, where lambda is some dominant co-character. And then we can produce the closure. So the affine Schubert variety will just be the closure of this cell inside the affine Grassmannian. So Ger G lambda bar, the closure, this is just Ger G, well, okay, yes, it's the closure. I should also say, perhaps, there's a stratification of the affine Schubert varieties. So stratification, or the closure relations. Closure relations. So the cell Ger mu of G will appear inside the closure of Ger lambda G, if and only if mu is less than lambda in the dominance order on dominant weights. So this really means that lambda minus mu is going to be equal to a positive integral sum, or a non-negative integral sum, ai alpha I check. And mu is going to be a dominant co-weight. Okay. These affine Schubert varieties have a T action. So we have a T action, the torus, the C torus will act on Ger lambda bar G. And the torus fixed points of this projective variety are precisely the points that I had in my notation. So the T fixed C points are precisely the T to the W mu, where, or at least they're cosets, where W is in the Weil group and mu is less than or equal to lambda in the dominance order. So I can take a dominant co-weight and then take all of its W translates. These will be precisely the T-fixed closed points of the affine Schubert variety. Okay, I believe I have all the background I need. Any questions here? Okay, so next what I want to describe is this result of Franklincot in 1980. So Franklincot, 1980. I need to introduce a little bit more notation. So I'm going to write H for the basic representation. So this will be equal to the restricted dual of the cohomology, zeroth cohomology of Ger G L dual. So this is what I call the basic representation. You take the ample generator, you take the zeroth cohomology, and you take its restricted dual. This is the basic picture of a representation of an affine algebra or of an affine Kac-Moody group. And then we need a what's called a homogeneous Heisenberg algebra. So I'm going to write T hat to be equal to, here T is the Lie algebra of the torus that I have above. So I take the K points and then I add a central piece. This is kind of bad notation, but I'll call my central piece K, but without the loop. So this is a central extension of the K points of the Lie algebra of the torus. So this will be called the homogeneous Heisenberg algebra. And the bracket here comes from taking residues. So maybe I'll write this really quick. X of f bracket y of g is going to be equal to, so I take the normalized form on x and y times residue t of dg times f k. Okay, so it's a central extension of this infinite dimensional algebra. Now, what the theorem of Franklincot states, hopefully this still appears, is the following. So the theorem of Franklincot is precisely that the basic representation H will decompose into a big direct sum over all lambda inside the, oh, by the way, this is in types ADE. So this is a simply laced type, this is a simply laced phenomenon. In types ADE, the basic representation will decompose into a big direct sum of Fock spaces, where these are going to be in the root lattice. So I sum over the root lattice, and for each element of the root lattice, I have this pi lambda, which is going to be a Fock space. So by a Stone-von Neumann type theorem, we have a very nice parameterization of all of the irreducible representations of a Heisenberg algebra. And these are exactly appearing here as this, this big direct sum of Fock spaces. These are nicely described as induced representations as well. Okay, so this result in types ADE this was done in about 1980. And Xinwen Zhu generalized this and made this into a more geometric statement in about 2007. And it's that statement that I want to discuss briefly right now. 1 second. Yeah, okay. So here's some work of Zhu in 2007. What I want to first consider is I want to consider the T-fixed subscheme of a given affine Schubert variety. And if I do, I will have a restriction map from global sections on Ger G lambda bar L. So this is the space of global sections. Here I'm restricting my line bundle to this affine Schubert variety, take global sections. There's going to be a restriction map to global sections H0 on Ger G lambda bar. And now I tensor with the structure sheaf of the T-fixed subscheme. So O Ger G lambda bar T-fixed subscheme tensor L. So here you should just think of restricting this line bundle to the T-fixed subscheme of the affine Schubert variety. Okay, we have such a map. And the work of Zhu says that in types A and D, This map is an isomorphism. This is the results that we will generalize. So I want to kind of discuss some things about this. So some remarks.
May I jump in again? This
Absolutely.
is every lambda. So this
every
is
lambda.
For each
every
lambda.
dominant co-weight.
All right.
We have this
okay.
isomorphism.
Okay, thank you.
Yep. So some remarks. The first remark is that this, as stated, is for A and D, but it often works in type E as well. So often holds in type E, E6, E7, E8. There are some missing cases. So, but it's expected to hold for all co-weights in type E as well. So this is an expected result. It's just not proven yet. Another remark is that this requires the non-reduced structure. Non-reduced structure. In other words, I'm not taking the T-fixed subvariety, which is just a discrete set of points. I'm taking the T-fixed subscheme of this affine Schubert variety, which is a non-reduced scheme supported at a discrete set of points, namely the C T-fixed points of Gur lambda. And then another remark is that this implies the Frenkel-Kac theorem. And the way to see that, roughly, is to know that the T-fixed subscheme of the whole affine Grassmannian, this is going to be isomorphic to the affine Grassmannian for the torus. And so what you can do in this situation is if you have this isomorphism for all co-weights lambda, all dominant co-weights lambda, you can take limits. And then what will appear here is global sections of L on the affine Grassmannian being isomorphic to global sections of L restricted to the T-fixed subscheme, which is the same thing as global sections of L on the affine Grassmannian for T. And then this decomposition, writing L as a space of sections, or the space of sections of L over Gur T, will precisely yield the direct sum into Fock spaces that I had before over here. And now I should probably say just a couple quick remarks on the proof. I don't want to talk too much about this, but so here at least is the idea or the overall sketch of the proof. And so two other things that I'll remind you of is that, first of all, this only works as proven in types A and D, and it's expected in type E. And also this only is involved with L, the ample line bundle of central charge 1. I can't take arbitrary line bundles of higher central charge and have this theorem work. More stuff will appear. Okay, a sketch of a proof. So
when you say more stuff will appear, is it known precisely what stuff will appear, or is it?
Yeah, that's known. So essentially, what the phenomenon that's happening here is that all of the maximal weight spaces in the representation are all in one orbit of the affine Weil group. The moment that you get to higher representations, you will have more stuff inside the dominant chamber, and then you'll have to take the affine Weil group translates of all of those things, and you'll have Fock spaces associated to all of those things appearing. Yeah. So the sketch of a proof roughly goes as follows. So we can get a short exact sequence of sheaves on an affine Schubert variety. 0, so I lambda, this will be the ideal sheaf of the T-fixed subscheme. This will include into the structure sheaf Gur G lambda, and the quotient sheaf will be the structure sheaf lambda g t fixed. And associated to this short exact sequence of sheaves, we can take cohomology and we produce the long exact sequence with the first terms. Oh, and we're twisting by the ample line bundle. So we'll have global sections on ger g lambda bar of I lambda 1. So this 1 means twisting by the ample generator into global sections on the affine Schubert variety associated to lambda of L, the ample generator, mapping to global sections on ger lambda g of L tensored with the structure sheaf O T. I won't write it all out here. So we have this, these are the first terms of the long exact sequence. And there will be more terms, but the point of the proof is to show the following things. So the first step is to show that this map pi, this restriction map, is surjective. So showing that pi is surjective, this just comes from essentially taking dual spaces, which will be affine Desmajor modules, and taking limits. And then essentially this is the piece that's closest to Frenkel-Kac's. You take the limits over these, you know what the irreducibles are on either side, and this being a surjection means that on the dual spaces you have injections. So this is saying we have an injection from a bunch of direct sums of Fock spaces into this space. Okay, so the first step is to prove that pi is surjective. Once you prove that pi is surjective, you want to prove kind of a reduction lemma. So step 2 is a reduction lemma, which says if this space vanishes for lambda and this space vanishes for mu, where lambda and mu are dominant co-weights, then this space will vanish for the direct sum, for ger lambda plus mu. And so that reduction lemma uses some flat degeneration techniques and Balint and Drinfeld-Grassmannians. And what that does is that reduces this problem to checking the vanishing of this space on all fundamental co-weights. And then it's a case-by-case check.
Now,
and so
let me jump in again. So your proof involves effectively showing H0 vanishes, right?
Yeah, showing that this vanishes.
But
and
you're
that
not claiming that H1 of that sheaf vanishes, because that would prove surjectivity too.
That's true. That is a consequence of surjectivity. So we don't prove that H1 vanishes, we prove surjectivity, and then this vanishing will be a consequence of the fact that higher cohomologies of these terms always vanish. These are affine schemes, and we have a Borel-Bott type theorem here, which says higher cohomology vanishes. So it's actually a consequence. Also, this is all work of Zhu still. Has that answered some questions?
Yeah, I mean, the natural way is to show that the H1 of the I lambda sheaf vanishes, but you don't know that a priori.
That's correct.
Oh,
That's
I
correct.
see. Okay, all right, thank you.
Mm-hmm. And so after the reduction theorem, it boils down to checking this vanishing for lambda dominant fundamental co-weights. And this check is completed in type A and type D, and it is not totally complete in type E. There are some dominant fundamental co-weights which are missing. So that's why the theorem is not yet known to hold in the generality that it should. Okay, so this is the result that we aim to generalize. Any further questions before I proceed? Okay, so another fact is that this theorem cannot generalize to the non-simply laced types. So I cannot have this theorem for affine types B and C, or G2 and F4, but we can generalize this type of result to twisted affine Grassmannians. So now I want to introduce twisted affine Grassmannians. So twisted affine Grassmannians will be associated to automorphisms of the reductive group G. So associated to twisted loop groups. So the construction is as follows. So for the simply laced type ADE algebras, there are certain automorphisms of the Dynkin diagrams that induce automorphisms of the algebras and of the associated groups. These are the diagram automorphisms. So for type AN, you have an order 2 automorphism if n is greater than 1. For D4, you have an automorphism of order 3. For all type D, you have an automorphism of order 2, which exchanges 2 of the leaves. And then for E6, we have a diagram automorphism of order 2. One strange thing that we must do is we would like to build these twisted loop groups out of the diagram automorphisms, but in one case we must alter our automorphism. So in type A2n, so this is going to correspond to a non-split group. In type A2n, we have to modify the automorphism, and I can tell you how we modify it. We modify its action on the Chevalier generators. So the action on the root spaces is exactly as you expect, but on the middle 2 nodes, namely on nodes n and n+1, the action on the Chevalier generators picks up an I, a root of -1, square root of -1. And so this new automorphism that we define is now order 4 instead of being order 2. So I'll explain later why we make this kind of strange choice of automorphism. But once we have our automorphisms in hand, we can define our loop groups. So we let sigma act on, say, k by sending t to a root of unity times t. So we're changing the uniformizer of k by multiplying by a root of unity. And then we can form the twisted loop group. And it'll be exactly gk sigma. For now, the sigma acting simultaneously on the group and acting on the field of formal Laurent series k by acting on the uniformizer. And on the level of C points, we can define the twisted affine Grassmannian in the same way. So definition, the twisted affine Grassmannian, which I'll write Gur beautiful G, at least on the level of C points, this can be given as G of K sigma fixed points mod G of O sigma fixed points. So this is a very similar construction to the affine Grassmannian. I'm just using these twisted loop groups and twisted arc groups, if you will. Is this okay? Yep. Okay, so what I want to kind of race through, since I only have 15 minutes left, is first to mention, okay, let me skip. So let me get just to some facts. I'll just mention there's also a moduli description of this affine Grassmann, of this twisted affine Grassmannian in terms of G-torsors for a non-constant group scheme over the formal disk. And that does play a role in the proof, but I do want to kind of get to results. So some facts that are very similar to what we had in the untwisted case is that the twisted affine Grassmannians are in schemes, and they're in projective. Once again, we have a stratification. So here, the stratification is going to go as follows. Gur G will be equal to a disjoint union over, now it's going to be what I'll write as lambda bar inside the co-characters of T. I take the co-invariant lattice and I take the dominant elements there. And then I have a decomposition into cells, which I'll just write as ger lambda bar, beautiful G. So I'm sweeping a fair amount under the rug, but at least formally, this looks very similar to what we had with just the untwisted affine Grassmannian. We're just kind of playing around with the parameters. Okay, so we have a stratification like we want. Once we have these twisted Schubert cells, we can define the twisted Schubert varieties by taking their closure. So definition is that we can take ger beautiful G lambda bar. So this is the twisted affine Schubert variety associated to lambda bar, which is the image of lambda inside the co-weight lattice. This is just going to be the closure of the cell inside the twisted affine Grassmannian. And then we also have some results as follows. The Picard group behaves similarly. So the Picard group of the twisted affine Grassmannian is also isomorphic to the integers. And once again, and so we can take an ample generator L. And once again, we have a central charge homomorphism, C, from the Picard group of the twisted affine Grassmannian to Z. And once again, the central charge, you probably can't see this, the central charge of the ample generator is once again equal to 1. This is precisely the reason why we needed to take the strange automorphism in A2N. This fact is no longer true if you take the diagram automorphism. You'll actually have a ample generator of central charge 2. So this is sufficient reason for us to take our altered automorphism of G to get this fact about central charges being 1 back. And once again, we have a description of the T fixed points. These will be associated to the n lambda bars. So I'll just write the T sigma fixed points are these classes, which I'll write as n lambda bar. This is just kind of a very similar story to in the untwisted case, where the fixed points are parametrized by really W orbits of dominant covariant elements in the co-character lattice. Okay, so at the very least, I hope that even if this might not be so familiar, at least structurally, it looks very similar to what we were having in the untwisted case. And here, at least, I can formulate my results with Juzu. So once again, we can have the following theorem. And this is due to myself and Professor Juzu Hong. Once again, we can consider, for the ample generator, we can consider a restriction homomorphism from global sections on the twisted affine Schubert variety, L. This will map to global sections of the restriction. So now we restrict L to the T fixed subscheme, T sigma fixed subscheme, sorry. There's now just a sigma action. So this is essentially the same statement that we had in the untwisted case. I hope that you can still read this. Maybe it's being cut off a little bit. And the result is as follows, that for types A to n twisted, A to n minus 1 twisted, for D for 3, and for D2 with n greater than or equal to 4, in these cases, pi is an isomorphism. Okay, so in this sense, this is a generalization of the result of Zhu to the twisted case. Some remarks. One remark is that, so this often holds for E6 twisted as well. There's, in particular, there's one collection of dominant co-weights that cause problems, but for all the other dominant fundamental co-weights, this is known. So this is expected to hold always in E6 twisted, and it holds often. Another thing, and I didn't really mention this when I was talking about the earlier work, but this gives us information about the smooth locus of these twisted affine Schubert varieties. So as a corollary, at least in types A 2n-1 twisted and D4 twisted and D n greater than or equal to 4 twisted. In these cases, we gain as a corollary that the smooth locus of the twisted affine Schubert variety is precisely the cell, is precisely the cell for lambda bar. So this sort of result was already known in the untwisted case by different methods using perverse sheaves and intersection cohomology due to Malkin, Ostrich, and Vibornov. But this can be reproven using this more de Mesure style approach. And in the twisted case, this result is new. This information about the smooth locus of the twisted affine Schubert varieties. So I have 5 minutes left. I can talk a little bit about the proof. Any questions, by the way?
So why does this not tell you anything about the A2n case?
It actually tells you quite a bit about the A2n piece. There's just one issue. It has to do with the map to the co-invariant lattice, and in the A2n case, there's kind of some bad behavior where let me make sure that I get it correct. It's a bit delicate. I believe it's a case where one particular simple co-root must map to actually twice what you expect. So there are some strange multiples that fly around, and what that messes up is that if you have an affine twisted Schubert variety and you look at the strata that looks like, say, lambda minus that particular, like half that co-root, then we don't gain information there. But we do gain information for almost all of the other cells underneath. So it doesn't hold in this, or we don't know that it holds in this total strength. There's essentially one small issue in the A2n twisted case, but we can still say quite a bit about the singular locus in the A2n twisted case.
I see.
It's something delicate about this co-invariant morphism, basically.
Okay.
The combinatorics there. Mm-hmm. So maybe I have 3 minutes to do a brief sketch of the proof. So a brief idea. Is that we really want something global. So we create a global affine Grassmannian, global I'll write it ger G bar. This is now going to be a an in-projective scheme over P1. So this is built by taking a non-constant group scheme over P1 and then taking the construction of the affine Grassmannian using G torsors. So we create a global group scheme, and this has the following properties. The fiber over, so I'll write it ger global G P, when P is equal to 0 or infinity, this is going to be isomorphic to the twisted affine Grassmannian, ger beautiful G. And when P is not equal to 0 or infinity, then the fiber of this global affine Grassmannian over P will be an untwisted affine Grassmannian, ger G. It'll be isomorphic to just ger G. So we have this kind of global situation, which allows us to translate information from the untwisted affine Grassmannians to the twisted affine Grassmannians. And once again, in this setup, we can build a global line bundle, L, such that when you restrict L to each of the fibers, the line bundle that you get on each of the fibers is precisely the ample generator on each of the fibers. So when I restrict this global line bundle L to a fiber where P is away from 0 and infinity, it's the ample generator for the untwisted Grassmannian. And when I restrict this line bundle to the fiber over 0 or infinity, I get the ample generator for the twisted Grassmannian. So the construction of this line bundle involves twisted conformal blocks and some work of Professor Hong and Professor Kumar. And then lastly, we produce global affine Schubert varieties. Which I'll write ger global G with this bar underneath to denote global lambda. So these global affine Schubert varieties are now projective varieties over P1. So this is going to be a flat scheme over P1, such that this will provide a flat degeneration from the untwisted Schubert variety associated to lambda and the twisted Schubert variety associated to lambda bar. And now we can, since we have a flat scheme, and since the T sigma subscheme, there's a global T fixed subscheme in here, and the fiber of this global T fixed subscheme away from 0 and infinity is just the T fixed subscheme, and the fiber here is going to be the T sigma fixed subscheme. So we have this flat degeneration from the T fixed subscheme of the untwisted affine Grassmannian to the T sigma fixed subscheme of the twisted Grassmannian. And what we have then is that, I'll just write this as my last line, is we can use flatness to show that global sections, if H0 ger G, the ideal sheaf associated to lambda 1, if this vanishes, then we will show that global sections on the twisted affine Schubert variety, ger beautiful G, lambda bar closure, and now I'll write this I lambda bar 1. This must vanish as well by using a flatness argument and some information about Euler characteristics of these ideal sheaves and restricting to different fibers over P1. I think that's a sketch of the proof, and I'm now over time, so I should stop now and ask for questions.
Any questions?
Yeah. So of course your projection, your global guy, ger G over P1, I guess that's a flat morphism.
Yep.
And your line bundle, basically you're taking the, well, I don't know what you want to call it. I would call it P lower star of L. I mean, the global sections.
Yeah, exactly. That's correct. Yeah, on a Schubert variety. Mm-hmm.
Yes, and basically you're claiming a base changing argument that you can compute. You know, this is very classical in ordinary algebraic geometry of a flat morphism, and you have a coherent sheaf, and you want to take the fiber of the pi lower star, and you're saying that you can prove those theorems that you have.
That's correct. That's correct.
Yes. So your stock at pi lower star of L, or whatever you call it, at T, is in fact H0 of what you expect it to be. So you have a base result like that.
Precisely, yes.
Okay.
And now it's true that flatness alone, if I just say flatness, that's not quite enough, because flatness just has upper semi-continuity with respect to the dimensions of sections. But flatness also preserves Euler characteristics.
Yeah.
So we can use some...
Yes, you need some vanity. I understand this. So the classical theorems, you need some kind of local freeness of the sheaves. These are standard base changing arguments that you can find in EGA or whatever the hell. And so they're general. Of course, the Euler characteristic is constant, but
Precisely.
the individual sheaves may jump. But on the other hand, if you have some local freeness, then you can conclude a good specialization argument. And that's basically what you're doing?
That's correct. Yes, that's precisely what we're doing.
Okay. Now, one other question. You were mentioning the word torsor over spec, over the disk. Now, I assume you meant torsor for the Zariski topology. Which topology are you talking about?
This should be taken, since I'm working over C, this should be taken in the étale topology.
So this is the other question I was going to ask you is, which topology are you working with here?
Yeah, so for these constructions of these affine Grassmannians, you should be, if you want to write them as quotients, you should write them as quotients either in the étale topology, or if you're working with a more complicated field over characteristic non-zero, you may need FPPF or FPQC.
Okay.
But at the very least, yeah, I'm working in the étale topology.
Yeah, and I suppose you could replace that power series ring by the Henselization of, I mean, in other words, you had C power series in T. Right?
Yes.
Yeah,
right.
and you can look at the subring of the Henselization, the Henselization of, C of 0. The reason I ask that is you have these basic theorems of Mike Artin about approximating things in Henselian rings. In other words, C double bracket T, I don't know how essential it is to your arguments, but I don't know if it's true that you could replace that by the subring, which is the Henselization of the C of T at the origin.
So I am not too familiar with that.
Okay.
I don't think I can give you a good answer there.
Yeah, I mean, since you mentioned the étale topology, that is exactly the local ring that you work with in the étale
right.
topology, the Henselization. And Mike Artin's approximation theorem says basically you can approximate any structure in a power series ring by by these Henselian things. I don't know whether that helps or not. The only advantage of the Henselization is that it's built up out of étale covers from finite. Well, you go from the disk C of T, and then you look at the étale covers and you take the this is the completion that you work with in the étale topology rather than working with just the power series. But I don't know if it makes any difference. It's just kind of an idle question.
So it was somehow my impression that the C double bracket T formal power series should be Henselian. Is that am I wrong?
Absolutely it is.
Yeah, it is. So
it's too big. It's not the Henselization. In other words, if you go back down to the disk, just C of T, right? Right. And then you Henselize that ring, you get a much smaller ring that consists of power series which are algebraic functions. This is the one you work with in the étale topology. And I have no idea now you mentioned that some of these people were doing things with the étale topology. I have no idea what they've done. It's kind of an idle question. And I don't know whether if it makes the slightest bit of difference to what you're doing.
So I would say that stuff is definitely something that I should know, essentially, because to get into the deep algebraic geometry of these constructions, that's the language that I would need to use. Fortunately, I'm able to describe most of these things just purely using representation theory, because all of these spaces of sections have very nice descriptions as affine de mesure modules. So you're absolutely correct that that is the correct language and way of thinking about these constructions, though. That's certainly
Right.
correct.
So if you replaced your complex numbers by, let's just say Q, then Henselizing, you should be including all the finite extensions of Q, and I would guess that you're getting representations of a Galois group of Q bar over Q. I'm just conjecturing. I'm just asking ignorant questions here. I mean, in other words, you can, of course, you're ignoring the arithmetic. You're just looking at C double bracket T. Well, what if you do Q double bracket T?
Yeah, so
and then,
that,
of course, the thing you should be looking for, or Q bar, my belief, I mean, it's sort of idle again. Wouldn't you be getting actions of Galois group of Q bar over Q on all your structures?
if I constructed these twisted groups by involving an automorphism of the correct order and then making a twisted group by combining an automorphism of the disk by that automorphism on my Lie algebra, then I could definitely construct such kinds of interesting twisted loop groups that should be giving me very interesting information. I agree with that.
My question is a little different. I mean, even go back to the untwisted case.
Mm-hmm.
But start your work over Q double bracket T.
I don't know too much about that. I can say, yeah.
All right, so this is just something to ponder in Beijing or something.
I absolutely agree. Yeah. So in Beijing, I'll be working. Apparently, my work will be close to someone who's doing some Schubert variety stuff. So I will need to pick up thinking about things over Q kind of rapidly. But at the moment, this work has been done entirely over C, basically.
So I had a question in a different direction. So does this theorem of yours give, well, basically some Fox-based decomposition, as in the Frenkel-Kac?
Yeah, if you take the limit, so say we're in one of the types where this isomorphism is known, then what you'll get precisely after you take the limit over, right, you write the twisted affine Grassmannian as a limit over these twisted affine Schubert varieties, and then you'll precisely get that the basic representation, maybe I'll write it H sigma, will precisely decompose into a direct sum of Fock spaces, where now these are Fock spaces for the sigma fixed torus. Yeah, so this will once again decompose into a big direct sum of, now I'll do it like lambda bars, basically, where now I'm dealing with, I don't want to say anything wrong, but maybe it's sigma invariance. There might be something that I'm missing with invariance and co-invariance, but the type of statement that you get about Fock spaces is still true. Now that these will be Fock spaces associated to, so you take the TK sigma fixed points, and then you add a central piece, and then you build Fock spaces for this twisted homogeneous algebra, homogeneous Heisenberg algebra, and then that's precisely what will appear here when you take the limit. That's correct.
And so is this is something that was known to Frenkel and Katz, or is this something that one gets new from this?
That is a good question. I don't believe that the work of Franklincot extends. So my impression is that I haven't seen a statement like this, but this definitely should have been known to experts since the 80s, I would guess. The idea that this type of construction should work for the twisteds is old.
Okay.
Yeah. One more quick comment. Technically, I shouldn't. What I did write for Frenkel-Kac is weaker than their full statement. So their full statement works at the level of vertex algebras. So there's additional structure that I ignored when I wrote down the Frenkel, this type of decomposition of the basic representation. So this probably should be called a weak Frenkel-Kac or something like that. But
okay.
But yeah, this sort of statement is still true.